Hey folks, this is Major Jones here to talk to you about binary arithmetic. So we're going to start to take our binary numbers and show how we're going to perform basic math operations on them, like how to add in binary and subtract in binary. And along the way, we're going to introduce a different way of looking at a binary number that lets us represent negative numbers. And we'll kind of start to see how we can build circuits to do these operations for us. Okay, so to start, I'm going to start here. On this slide, you can see a decimal addition and then the corresponding binary addition. And the thing to remember is that just like in decimal, if I were to, if you can imagine sort of adding these together, right, 5 plus 7, the result's 12. In order to complete this addition, what I do is I write the least significant value here, and then technically what I'm doing is carrying the 1, because that's, sort of one greater. And when I bring that down here, the result is sort of 12. In binary, I'm doing the same thing. I just got to remember that any number that exceeds 1, I have to carry, because that's 1's the largest value I can represent. So here you can see I've got 1 plus 1. Well, 1 plus 1 is 2 in decimal. The way I represent decimal 2 in binary is a 1, 0. So just like I sort of wrote the 2 here and carried the 1, over here when I add 1 and 1 together, I'm going to write the 0 and carry that 1. Now I get to add 1 plus 0 plus 1. The result of that is 2, so again I write a 0, carry the 1. 1 plus 1 plus 1 is 3 now. 3 in binary is 1, 1, so I write that here. I'm technically carrying the 1. 1 plus 0 is 1. And if you work this out, then these two should agree. So hopefully what I've done here is show indeed that 5 plus 7 is binary or decimal 12. Okay. So that's addition. And let's see, if I go back one slide, you'll notice that I can sort of represent, I can represent that like a truth table almost. So you can imagine here, what I'm doing is I'm doing x plus y, and the result of this is going to be some value, S sum, and with potentially a carry, right? So 0 plus 0 is 0, and I'm carrying 0. So that's this first row here. 0 plus 1 is 1 with nothing to carry. So that's, either of these two rows right here. 1 plus 1 is 0, carry the 1. That's this last row right here. And we'll start to see how we can, if we can, represent this mathematical operation, if we can represent addition as a truth table, then we can start to see how we might be able to build a circuit that performs this for us, but more on that later. Okay, let's look at subtraction. So here I've got decimal subtraction. I'm doing 13 minus 7. Okay. In this case, I do kind of like what I do with addition, right? I start with the rightmost column. Only in this case, I can't complete this, subtraction without borrowing. So, technically this 1 would sort of become a 0. I sort of borrow the tens place. 13 minus 7 is 6. When I subtract in binary, I might need to do the same thing. All right, so 1 minus 1, okay, that's a 0. That's pretty easy. 0 minus 1. I can't compute without borrowing. So what I'm going to do is steal from the next greater digit, right? So I can imagine that, this, I'm going to look at sort of this, the next greater digit, combine it with the one below it, and think of this as sort of like the value 2, right? So what I'm going to do is sort of change my... I'm going to borrow from this digit, so this becomes a 0, and I'm going to imagine that this has become a decimal 2. And I can't really represent a 2 in binary, but bear with me. I'm going to steal from this, so 1, 0 becomes, I'm going to sort of borrow that down, so 2 minus 1 is 1. Now I move over, this was a 1, but now it's a 0. 0 minus 1, I can't perform without borrowing, so I'm going to borrow again. This is going to become a 0. This is going to become sort of quote-unquote 2. 2 minus 1 is 1. 0 minus 0 is 0, and so I get the result 0, 1, 1, 0, which is 6. All right. So then if we go back to one slide before, you can see, again, I can sort of think of this in terms of a truth table. If I've got X and Y and I'm subtracting them, I got the difference and here, and then uh, B is my borrow column, is best thought of as being true if I need to perform the borrow operation. So 0 minus 0 is going to be 0, and I don't need to perform any sort of borrowing. 1 minus 0 is 1, and I don't need to perform any borrowing. So these are, these this row and this row. 1 minus 1, another easy one. That's 0 with no borrowing. So that's this last row here. 0 minus 1, this is the weird one. So recall that, here I am borrowing, so I'm in this row right here. And the result of this, this 0 sort of became a 2. The result of this was a 1. So my difference is a 1. I am borrowing. So in that sort of weird case where I'm doing 0 minus 1, that's this row here where I do need to sort of set that borrow bit. All right. More on how to turn this into a circuit later on. All right. If we're performing multiplication, again, the mechanics are very similar. So here, well, this is kind of uninteresting because these are single bit numbers, but let's say I had, 145 times 17. All right. Well, the first thing I'd write down here is, I'd take this digit, this least significant digit, and sort of multiply it across the top, right? I'd write out the result of 7 times 145. And then I'd do the same thing with the next most significant digit, only I'd sort of pad the right-hand side with a 0. And over here I'd write, 1 times 145, and I'd add down, all right? I do the same thing in binary, only actually it's a little easier since I only have zeros and ones. So to start with, I'm going to take this least most significant bit, 1, multiply it by the top, right? So I get 0, 1, 1, 0. This next one, if I were to write it in here, would be all zeros. So we kind of skip that step. And then here, and I've got another one. These two are sort of padding, right? Because this is in the, effectively the 4's place. So I had to sort of, it's 2 over from the rightmost. So I padded with the 2 zeros. 1 times this value is 0, 1, 1, 0. And then I just add down. 0, 1, 1, 1, 1. And hopefully what I've shown with this is that 6 times 5 is in fact 30. Recall this is 16 plus 8 plus 4 plus 2, which is equal to 30. All right. So the mechanics of multiplication, same as they are in binary as in decimal. And then lastly, we're going to look at long division. So the mechanics are the same. I'll work through this example here to kind of show you that that's the case. So 110, basically what I'm going to do is I'm going to start, I'm going to sort of move my way to the right until 110 fits into some value. So it doesn't fit into 0, it doesn't fit into 0, 0, it doesn't fit into 0, 0, 0. It's not until I sort of get here, right? I get 1, 1, 1. That is larger than my the value I'm dividing into it. So so I put a 1 here because I can fit one value in there. 1 times 110 is 110. Once I subtract, 111 minus 110 is 1. Then I bring down the next digit, 1, 1. 110 does not fit in 1, 1, so I write a 0 up top. And then bring down the next digit. 110 fits exactly into 110, so I put a 1 here. 110, I write that down here, and then I subtract it 0. So this is saying that 6 goes into 30 exactly 5 times. All right, so that's addition, subtraction, multiplication, division. The mechanics in binary are the same as they are in decimal. We just got to remember for addition that, I overflow a lot more quickly than I do in decimal. And when I sort of borrow and when I subtract, I'm stealing a bit from the next column over and sort of turning a value into a 2, even though 2 is not necessarily a number we can represent in binary. Okay, so let's talk about something called 2's complement. And let's see. You know what? I'm just going to give myself a little white screen here. Okay. So far we're familiar with let's take like a 4-bit number, right? I've got 0, 0, 0, 0, which we sort of equate to decimal 0. That I can increase all the way to 1, 1, 1, 1, and that's going to be equivalent to 15 in decimal. And that's definitely one representation of our binary numbers. We call this sort of an unsigned integer, or unsigned representation. But of course, using this, there's not a sort of baked-in way to represent something like -1 or -8. So in order to do that, we're going to use a method called 2's complement. And to do that, what we imagine, we'll take the 4-bit number, for instance. I've got 4 bits here. In my unsigned numbers, these columns were weighted differently, right? The rightmost column was my ones column. Next over was my 2's column. Then it was my 4's column, and lastly my 8's column. In 2's complement, we're going to do, the only thing we're going to change is the sign of the most significant bit. So this will still be my 1's column. This will still be my 2's column. This is still my 4's column, but this is now my -8's column. All right. And by changing that most significant bit to a negative, now I can actually start to represent negative values. You can imagine, if I have a 1 here, 0, 0, 0, this is equivalent to -8 plus nothing, right? So -8. 1, 0, 0, 0 is -8. If I have 1, 1, 1, 1, this is equivalent to -8 plus 4 plus 2 plus 1, which is -1. And so for my 2's complement, the best way that I kind of think about this is I've got 1, 0, 0, 0 kind of all the way at the bottom, -8. This goes up to 1, 1, 1, 1, which is -1. 0, 0, all zeros is 0. And the greatest positive number I can represent with 2's complement is all ones with a 0 in front. 0, 1, 1, 1 in this case is +7. So I still have 16 values. I can still represent 16 different numbers. I just basically sort of move that number line around. So instead of being able to represent the range 0 to +15, now I can represent the range -8 to +7, and I can actually do something kind of interesting with these negative values. One thing to note about 2's complement is that there's nothing specific. There's nothing special about the 8's column. It just is that this is the most significant bit, and so that's sort of the column that becomes negative. So in 2's complement, it starts to matter exactly how many bits we're talking about. If I wanted to represent an 8-bit number in 2's complement, then I'd have my 1's, 2's, 4's, 8's column, 16's, 32's, 64's, and this would be my -128's column. So in 2's complement, whatever is the most significant bit is the negative value, and that changes based on how wide we're talking about in 2's complement. So when we start using signed numbers in binary, it's very important that we know kind of what's the width of that number, how many bits are we using to represent that value. Okay. Okay. There's a neat trick to be able to convert a 2's complement number from positive to negative, which you can see here. And the steps are simply I don't want that. To negate the binary number, so let's change all the zeros to ones, all the ones to zeros, and then add 1. All right, so for example, let's say we had our value, 1, 0, 0, 0, which was -8. Actually, no, I'm not going to do that one. That's actually, sorry, that's a... Pardon me, folks. Okay. Nope. Okay. I'm back. All right, here's our 2's complement. We are negating and then adding 1. So let's take our value. Let's do -1. 0 to 1, 1 to 1. Recall was, oh, dang it. One, 1, 1, 1 was the value -1. Okay, so if I first negate this, all my ones become zeros, and then I add 1 to that, I get the value 0, 0, 0, 1. 0, 0, 0, 1 is in fact +1. So this is showing how I might change this. In fact, I can use the same procedure to go the other way as well, right? So if I take +1 and I switch all the signs, 1, 1, 1, 0, and then I add 1, 1, 1, 1, 1, this is the value -1. Okay, so I can use this sort of flip the ones to zeros, zeros to ones, and then add 1 to the number to change a positive to a negative to a positive, either way. Okay. So we can use 2's complement now to represent negative numbers. So we can do all of our math stuff with 2's complement. And in fact, we can do something a little we can do something to simplify the subtraction. So you can see here that I'm trying to subtract 13 from 8. And before when we were doing the subtraction, honestly, that was like borrowing was a little bit of a mind. Well, I'm not going to curse. It was difficult, right, to figure out how to do that whole difference thing. What we can do now in this case is instead of thinking this is 8 minus 13, we can pretend it's 8 plus -13, which mathematically is the same. And now that I can represent negative numbers, all I need to do is take this number here, 13, make it negative, and then I don't need to subtract at all. I can actually just perform addition to complete this mathematical operation. So if we take this value here, we're going to, number one, invert the bits. So I've got 1, 1, 1, 1, 0, 0, 1, 0. And then I add 1, 1, 1, 1, 1, 0, 0, 1, 1. This is the value, -13, that you can see down here. Now I perform addition like normal. 0 plus 1 is 1, 1, 0, 1, 1, 1, 1. And what I should get is the value -5. The easiest way to check this is to do our little inversion trick, right? So if I take this value and I invert everything 0, 0, 0, 0, 0, 1, 0, 0, and then I add 1, 0, 1, 0, 1, this is +5. So if the inverse of this number is +5, then it has to be -5. And we can also confirm that if we actually did our math, right? If I did -128 plus 64 plus 32 plus 16 plus 8 plus 2 plus 1, that value is also going to be equal to -5. All right. That's a lot. Okay, so at this point, you know how to do binary addition, subtraction, multiplication, division. I've shown you how to represent negative values in 2's complements and how we can use the negative of a value to do subtraction a little more easily. You can see on the slide here that I can start to take these truth tables for addition and form them into circuits. So this is a little kind of sneak peek of our next lesson about how we can actually build circuits that do these math operations for us. That's all I got. I'll see you in class, folks. Have a great day.